Okay, this is Derek Thompson, and I'm doing exercise 43 in section 1.2 of the Stewart calculus book. What they want you to do is they want you to use these two functions, and they want you to do some compositions: f composed with g, g composed with f composed with f, and g composed with g, and find their domains. So what I'm going to do is I'm going to do f composed with g and f composed with f, and leave the other two to you. So first let's do f composed with g. So let's think about that. So f of x here is x plus 1 over x, and g of x is x plus 1 over x plus 2. So if I want to think about f composed with g, I think about f of g of x. G of x is now the input for f of x. So everywhere I see x in the expression above for f of x, I replace that x with x plus 1 over x plus 2. So this expression is not really simplified, but I have no desire to simplify it. Simplifying can be a bit of a danger when you're trying to find the domain, because this is the original expression, and what I want to know is I want to know when is any of the denominators that I see 0. That is our problem for rational functions. Well, the first thing is that if you look at the first term, you see that x plus 2 is in the denominator. So that means that minus 2 is a bad point of the domain. So I'll cross it out, because minus 2 would make that denominator 0, and also if you look at the denominator of the expression in parentheses on the bottom right, minus 2 would make that denominator 0 as well. But you also have to think about the fact that what I have in parentheses is a denominator. That fraction is the denominator beneath 1 in that complex fraction. And so if I make x plus 1 0, that would mean that I would be dividing 1 divided by 0. So I'm talking about right here. If I make that 0, then I would have 0 divided by x plus 2, which would be 0. And then I would have 1 divided by 0, which is not allowed. And that would happen when I make x minus 1. So that is also not allowed, because those are the two numbers that make denominators that I see 0. So the way I would write this domain is that I would write either set notation, which would be x such that x is not equal to 1 or 2, or I could write set notation, interval notation, which would be minus infinity to 1, union 1 to 2, union 2 to infinity. So that would be the domain for f composed with g. And I don't need you to simplify the expression. My rule is if the directions don't ask you to simplify, then you don't need to simplify. Not to say that I won't ask you occasionally to do so. So now the next part is f composed with f. So that's, again, f of x here is x plus 1 over x. And so this is a little tricky. F composed with f just means I write f of x. And so anytime that I previously saw x, I write that entire expression instead. So the first x, that's going to just become x plus 1 over x. And then the second time I see x, which is in that denominator, I'm going to change that whole thing to x plus 1 over x. Right there. And again, it's not simplified, but I need to figure out some problem points in my domain. So first off, if you look at the first term, there's no denominator, but the second term, 0, would make that a 0 denominator. So 0 is out. And it also would make this denominator right here, just the little 1 over x, it would make that 0. So it's a problem in two places. But I also have this entire denominator here. This is all under the 1. So that entire expression there cannot be 0 either. So I need to solve and figure out when is that expression 0, which may be never, but we need to check. So I need to know when x plus 1 over x is equal to 0. Well, remember I said never to divide by a variable, but you can multiply by a variable as long as you check whether you're introducing a redundant answer. So I'm going to multiply by x. I'm going to get x squared plus 1 equals 0. However, when I solve that, you know that you only get imaginary roots here. So there's no solution, which is good. That means there's no more problem points in the domain. So the only problem is 0. So the domain is either x such that x is not equal to 0, or I can write minus infinity to 0, union 0 to infinity.